just to confirm quickly, you can see the slides now, correct?
Correct.
Okay, excellent. Yeah, thanks everyone for joining. I'm an assistant professor at the University of Washington, and I work broadly in machine learning, often with a focus on datasets. And today I want to tell you a little bit about a project my group has been working on over the past year about improving the state of the art in multimodal datasets. Okay, so let's start with the basics. What's a multimodal dataset? For the purpose of this talk, a multimodal dataset is going to be a large collection of image-text pairs. So one example of a widely used multimodal dataset is Lion 5B, which, as the name suggests, contains 5 billion image-text pairs. Here are 4 examples of the dataset: the image, the green chair here, and then a corresponding piece of text that is crawled from the internet, green apple chair. And then a picture of the dog here with a sunset, and then the caption is sun, snow, dog, and so on. And when you look at this, you're maybe saying, the captions aren't the greatest, but this is typically the case for web harvested data. If you can get a lot of it, even with like mediocre data on average, this is still going to allow you to train very good models, because these large multimodal data sets over the past couple of years have become one of the key driver of progress in AI. Many of the recent breakthroughs from the past few years, like image generation, probably you've heard of the stable diffusion models, DALL-E, OpenAI's CLIP model, OpenAI's recent GPT-4, all of these models are multimodal models that depend on large collections of image text data sets, such as Lion 5B, as training data. So this is really a core component in a lot of recent AI breakthroughs. Cool, so good. So we have data sets like Lion 5B. Why am I looking for the next generation of image text data sets? And one of the, I think, big areas in machine learning now, where we know this is really important, data sets are really important, but we also know relatively little about how to build good large pre-training data sets. Like currently these data sets like Lion 5 billion are sort of like one-time efforts, a big web crawl that a team does once, and then we have all of this data, but we don't really know how to improve the data set because it's so large, and we don't have a systematic understanding yet of how to improve our pre-training data sets. So what I want to do today is sort of like explain to you a little bit how we are going about this in my group on the research side, building and improving these data sets, and also just tell you that there's still a lot of room for improvement in multimodal machine learning on the training data side. Cool, so we'll do this in 2 steps. First part of the talk is going to be sort of like one case study where we've seen a big breakthrough in AI by better pre-training data sets. Specifically, we will talk about robustness to distribution shift in OpenAI's CLIP model. And then in the second part of the talk, we'll see what the open source community currently is doing in terms of building better multimodal data sets. Okay, so let's get started with the first part. And sort of like the high-level challenge that we are going to think about here in machine learning is that of reliable generalization. This is a core challenge because often when we take our research artifacts from our papers and our academic benchmarks and deploy them in the real world, machine learning doesn't work as reliably as we would like to. I think one sort of like key example, or good example here, is the self-driving cars. When the first self-driving car demos happened, maybe around 2015, everyone got really excited, and there were a lot of optimistic projections that by 2020, we would have a lot of self-driving cars deployed in the real world. And there has been nice progress, and this is clearly a hard challenge. Smart people are working on it. But we are not yet at a point where sort of like all cars are self-driving it. And this is just one example here. Other areas are healthcare, robotics, and since it's 2023, obviously also chat assistants, which still have many reliability challenges when it comes to problems like being factually correct or answering questions correctly. So one key challenge here often is how can we make machine learning more reliable? And in order to make this more precise, so we have sort of like a good experimental setup to study this scientifically, we are going to look at reliable generalization in the context of ImageNet. This has probably been one of the most impactful data sets in the history of machine learning. I guess many of you are familiar with it. Just to recap this quickly, ImageNet is a large image classification data set. So input is an image, and an output is one of 1,000 different classes. And like the classes in ImageNet, for instance, are like animals, like golden retriever, vehicles, and so on. Good. So this has been studied by lots of people in the machine learning community over the past 10 years. And we've seen a lot of progress in pushing up the ImageNet numbers, getting better and better models on this benchmark. But we are clearly not there yet in terms of reliable generalization. And one way that people have sort of like rigorously started to measure this precisely is by building new test sets that stress test the ImageNet model. So we take a model that is evaluated primarily in the context of ImageNet, but then we also evaluate it on a wide range of other out-of-distribution test sets. For instance, ImageNet v2, ObjectNet, ImageNet Sketch, and ImageNet R. So the idea is it's still the same classes as ImageNet, but we change something about the data generation process to make the distribution different from ImageNet, and hence see how well do the models generalize out of distribution. Cool. Okay, so let's quickly look at what the state of the art here was before OpenAI's CLIP model. And we'll do this in the form of the following scatter plot. On the x-axis, we'll have accuracy on the ImageNet test set. On the y-axis, we'll put the accuracy on an out-of-distribution challenge test set, such as ImageNet v2. And then every blue dot here in this plot is going to correspond to one model in our test bed. So here we ran about 80 models, 80 ImageNet models, and we evaluated them both on ImageNet and ImageNet v2. And we had a large library of models from this, ranging from the seminal AlexNet paper all the way over widely used architectures like VGG, ResNet, DenseNet, Inception, and so on, to the state of the art around 2020, which was an efficient net. Good. And what you see here is that the better models do better, but all of them see a substantial accuracy drop. So the dashed line here is y equals x. This is sort of like the ideal goal here. If you're not affected by the distribution shift, if you're a really reliable model, be on y equals x, but all of the models, all the blue points here, are below the y equals x line. There's a good linear trend here. You can fit a line to the blue points, and we can use this as our baseline for evaluating robustness. So basically, let's say you have a new idea for a new model, a new optimization procedure, a new architecture, and you tell me, okay, Ludwig, on ImageNet, I get 71% accuracy. Then I can look at this red line as a baseline, and I can see whether your model actually does better out of distribution than what we expect based on current models. So here on the y-axis, if you get 71% on ImageNet, the expectation would be that you get, say, 58% on ImageNet v2. And what we are looking for is ways of improving the robustness by going above this red baseline. This is what we call effective robustness. And the question, sort of like a research question here, was, how can we achieve effective robustness? And we know that this is a good target because humans have this property that they are on the y equals x line. So we did a study here with 5 expert human labelers, where we randomly shuffled ImageNet and ImageNet v2. And the human labelers are indeed exactly on y equals x. Good. So now the question was, do any current algorithmic techniques help here, right? Roughly speaking, we can divide machine learning into techniques that improve the training data and techniques that improve the learning algorithms. Let's see here what helped the most. So here, this is again the same plot, but I added more models to it. I added the brown points, which are robustness interventions, and I added the green points, which are models trained on more data. And what we can see here is all of the models are still suffering quite a lot from this distribution shift. They're not really moving far above the red line, but the more data models, the green points, do see some improvements in the sense that they are above the red line, at least by a little bit. So this was already promising. We'll see that there's a lot more to do with more data, but this was already some promising sign that more data can make better data can make your models more robust. And this is a similar story on many, many other distribution shifts. I mentioned a couple earlier: ObjectNet, ImageNet R, ImageNet Sketch. Here's a similar kind of plot for ObjectNet on the y-axis, larger accuracy drop now, but overall you still have this nice linear trend as a baseline. And the only models that stand out with a bit of robustness, a bit of lift above the red line, are the green points, which are again the models trained on more data. Good. So this was the state of the art as of end of 2020. And then something super exciting happened, which was that a team of great researchers at OpenAI started to tackle the same problem. And in early 2021, they released their CLIP paper. So title of the blog post here was Connecting Text and Images. They approached this from a multimodal perspective. And basically the first sort of like set of results they highlighted in their blog post was exactly these effective robustness comparisons. So clip VATL, the right column or the middle column here, is the new model that OpenAI introduced. The left column is a classical ImageNet trained ResNet one-on-one. We look at models that have matching ImageNet accuracy. So the right-hand column here is exactly, again, the effective robustness, the lift above the spaceline. And then we see that the clip model achieved really, really large effective robustness gains on all of these out-of-distribution shifts we just talked about, like +6%, +50%, +40%, and so on. And like in the research world, a small single-digit gain is something you can definitely write a nice paper about. And the clip model here achieved large double-digit gains. So this was really an unprecedented breakthrough in reliable generalization on these out-of-distribution test sets. Cool. And then they also had the scatter plot visualization in the paper. And again, the blue line here is the baseline, the ImageNet trained models. And then the orange line, which is much closer to y equals x, is the clip models from OpenAI. Okay, and this is super, super impressive. And an obvious question was here, what makes clips so robust? So this was one of the follow-up questions that my research group then addressed. And we wrote a paper about this, and the title gives it away. Data determines distributional robustness and contrastive language image pre-training. The idea was here in this paper, we went through all sort of like possible hypotheses for where this large robustness gain could come from, like language supervision, training distribution, training set size, loss function, test time prompting, model architecture, and so on. And then the cool thing is that you can actually rule all of these out in a very precise way, with the exception of the training distribution. So this is a very good example overall that having high quality training data is really, really key to reliable generalization. And yeah, going back now, sort of like to the high level theme here, the out of distribution story with the image and distribution shifts. So I think one very nice example that multimodal datasets are key for AI right now. Another story that happened in parallel that received also a lot of attention is text-guided image generation. I'm sure many of you have heard of DALL-E 2 or Stable Diffusion or Imagine. Basically, these pieces of software that can take arbitrary textual descriptions and then generate a corresponding image. And all of these are also powered by large image text datasets. Cool. Okay, so now we are convinced that these large image text datasets are really key. And how do we build them? So let's look at this next. So first, we'll have a brief look at Lion 5B, which is as we said, a large image text dataset that the open source AI community built. So my research group has been part of this together with many cool people in open source AI. And basically here our goal was, let's get started and build a good large image text dataset. Particular Lion 5 billion is 50 times larger than YFCC 100 million, which was previously the largest public image text dataset. Like many of these datasets, Lion 5B is crawled from the web. Specifically, we started with Common Crawl. There were about 50 billion image text pairs in Common Crawl. And then we built a filtering pipeline to sort of like, first of all, download all of this data, analyze it. And then the core filtering step was that we used an existing clip model in order to remove image text pairs where image and text were actually not that related. So the technical detail here is that we computed the cosine similarity between the image and text part. And then if it was below a certain threshold, we would remove that image text pair. Good. So let's see how well that works. And specifically as a quality check for the dataset, we were interested in how well can you train clip models on Lion. We know that clip models have all of these nice robustness properties. They've become very widely used. We wanted to build a dataset that enables us to train high quality clip models in open source AI. And we're sort of like good and bad news. The good news is overall it works quite well in the sense that for small to medium sized clip models like a B32 architecture, training on Lion gives basically the same architecture as training on the original OpenAI dataset, which is internal to OpenAI, but we can still compare the quality of the resulting models. The catch here is that as you scale up the models that you train, there's an increasing gap between what Lion enables you to train and what the OpenAI model achieves. So on ImageNet, this gap for a large model is about 3 percentage points. On an out-of-distribution test set like ObjectNet, it's about 9 percentage points. So overall, as I said, this was a great starting point for the community. Lion 5 billion, for instance, is the training set for the stable diffusion models. So overall, this had a lot of impact. but it was not quite there. And we knew in principle, you can do better. And I was very curious, how much better can we make these multimodal data sets? And this is now where DataComp comes in. As you said, DataComp is this paper that myself and my group and many great collaborators recently published. We built a benchmark for multimodal dataset design. So the idea is basically, let's redo Lion 5B from scratch, but now let's sort of like make the tooling reusable so that other researchers can explore their own ideas for building better pre-training datasets. And then we can rigorously compare which way of building this next large pre-training dataset works the best. Right, so like to contrast this a little bit, in traditional machine learning benchmarks, the dataset is fixed and we improve on the model side. In DataComp, we flip this around. Now the model training code is fixed and the participants are going to improve on the dataset side. Okay, cool. And the idea here is that this is going to enable collaborative dataset research similar to the model-centric research where we have good frameworks where people can build on each other's work. Cool. Okay. Concretely, how does this look? What do we provide as part of DataComp? So like the key artifact that we built is a large pool of candidate image text pairs. Again, sourced from Common Crawl. The largest version of our pool is 12.8 billion image text pairs. And then we go down by a factor of 10 a couple of times. And then we have, as we said, standardized clip training code and a downstream evaluation testbed of 38 tasks. And then what a participant does is basically take our candidate pool and propose a new way to filter this candidate pool into a high quality training set. This is one track. There's also another track where you can bring your own data source. If you have your own sort of like data source and you want to compare it to what's happening in DataComp, you can also do that. Cool. Okay. So this is what we put together as our sort of like competition or benchmark here. And then we also were just curious, how far can we push this with simple baselines ourselves? And the cool thing is that you can already start making rapid progress in improving multimodal data sets. So concretely, our first data set that we released as part of this overall paper already enables you to train better clip models than what OpenAI did. So concretely, if you now look at DataComp, previously Lion was 3 percentage points worse than what the OpenAI result. Now we are about 4 percentage points better. On ImageNet and also on ObjectNet, now we are 5 percentage points better. Previously, Lion was 9 percentage points worse. So overall, very nice gains. And this data set is already now in use at places like Anthropic, Apple, CMU, Meta, and so on. And another way to frame this is that the improvements here on the dataset side correspond to a 9x improvement on the compute side. So previously, if you had taken Lion, started with Lion, and you wanted to push your accuracy to 79%, you could do it, but it would require a larger model and training for much longer with more compute. And now you can get to the 79% with 9 times less compute than what Lion enabled. And since these models are really expensive to train, a 9x improvement in training cost is really big. Okay, and as we said, this is already in use by a couple of companies, and it was nice to see Andy Jones. He's a researcher at Anthropic. He emailed us a couple of months ago if he could send us a gift basket because he found DataComp so useful. Okay, cool. So we have only a couple of minutes left. Let's quickly talk about how did our new state-of-the-art data set sort of like come together. And there's sort of like 2 key components here. The one is that we improved the clip filtering that was already part of Lion, right? I mentioned it. In Lion, we use a clip model to filter image text pairs with low similarity. What we found was that the filtering in Lion was actually too aggressive. Letting in a couple more noisy examples turns out to be better because this enables us to, in the end, have a larger training set. On average, the data quality is a little bit worse, but having more data here of a little bit worse quality turns out to be better. And the other thing is we simplified the Lion filtering a lot. For instance, one part we could take out was the language filtering because it turned out that the clip model already knows well enough if it understands a certain caption or not. Okay, and then the second part here was image clustering. Basically, we removed images that in a clip embedding space are far from ImageNet. This is now not taking the text part into account, but we found that doing this basic quality control on the image side substantially improved the quality of the overall data set. And then the final DataComp 1B dataset is basically the intersection of the image clustering dataset and the clip filtering dataset. Cool. There's a lot more in the paper about scaling laws. This is obviously really key in machine learning nowadays, that you can make inferences about large-scale experiments from small-scale experiments. And we do that, and the multi-scale structure of DataComp enables that. We'd be happy to tell you longer about this, but we're almost out of time. So I'm just going to tell you sort of like what is the high-level research vision here right now. As we said, over the past couple of years, we have seen tremendous progress in AI with large models like GPT, Stable Diffusion, and so on. And one key component there are always these large internet harvested data sets. And this, at the moment, this is from a research perspective, still very much underexplored territory. There's a lot of cool work in traditional data-centric AI on making good task-specific, smaller-scale clean data sets that work well for one specific problem. What we currently don't really have a handle on the research side is how to do the pre-training of the large model in a good way, and specifically how to build these large internet harvested data sets for pre-training. So this is what my research group is really interested in right now and what we're working on. If you have any ideas on that, please reach out. We'll be happy to chat. For now, I'm going to leave you with the URL for our dataset competition, DataComp AI, and I'm happy to take questions. Thank you.
Thank you so much. That was really exciting to see the performance gains, that +4%, +5% from the DataComp training set. Very cool to hear that explanation of what you guys have been doing. We do have some questions coming in. So the first question here is, how could this approach be expanded across multiple languages or to other data modalities like PDFs or structured data like conversations?
Yeah, this is a good question. This is something we are starting to look at next. So obviously language, you don't need to do multimodal, even just language modeling alone. It's a really important area in machine learning right now. And we would now we're planning to transfer some of our lessons here to improving text-only pre-training datasets as well. So for instance, one thing we found useful in the multimodal context of Lion was this idea of using a clip model in order to filter a dataset. And the corresponding thing to do in the text domain would be, for instance, to use an existing small-scale language model and then use the perplexity that comes out of that model and threshold based on that in order to adjust what pieces of text to include and which to exclude. So yeah, I mean, this is still very early stages, but I think there's a lot of cool stuff to do here as well.
It seems like a lot of those similar ideas of the filtering can be applied across the modalities.
Hopefully, we'll see.
We'll stay tuned. Next year, you can present on that.
Exactly.
Okay, the next question is, how do you evaluate data quality? Is a larger data set always better, or is there a way to identify more salient data points?
Yeah, I think this is also very much at the top of our mind on the research side right now. More data is not always better. So one thing we found actually a couple of slides ago here with this DataComp 1B dataset that we put together. This is a smaller dataset than the clip filtering and the image clustering dataset by itself. So the improved clip filtering dataset was already better than Lion. It's about 2 billion images. The image clustering one is also 2 billion images. And then it turns out the best dataset is actually not taking the union of the two, but taking the intersection. So keeping only the images that are in both. This was a surprise to us, but yeah, I mean, in research, you need to explore things, try a couple of random ideas. And here it turned out that less data, but higher quality is better. On the clip filtering side, it was also that more data and lower quality is better. So I think there's just different quality notions that we haven't really disentangled yet. And I think, again, one research question is like, what does data quality exactly matter? We now have these different ways of quantifying data quality, like the clip thresholds, distance to ImageNet, and so on. And yeah, I would love to know the answer too.
Okay, our next question is, I find it interesting that clip is used both for filtering and cleaning Lion, and then later is used to check whether there is an improvement in performance. Is this intentional, or am I missing some reasoning?
Yeah, no, this is actually a really good question. So when we did this first in the context of Lion, this was just a pragmatic choice. We wanted to do some data filtering. Data filtering can take a lot of effort, so it needed to be automated. And we just started with this idea of using a clip model. And there was clearly a worry that when we use a clip model here for filtering, when we use this clip VATB32 for filtering, the worry was maybe we will never be able to train models that are better than the B32 model, which would be a bummer. But it turned out that you can actually filter with a B32 and then train models that substantially exceed the performance of your filtering model. Again, this is exactly why that worked. I think it's a good research question, but sort of like just sort of like empirically right now, this works better than expected. Yeah, so maybe just to answer my second facet of that question, why did we choose to evaluate the quality of a data set with CLIP? This was for two reasons. First of all, we have really good CLIP training code and open source AI with OpenClip. The CLIP models are relatively easy to evaluate. In the sense, there's a wide range of existing downstream data sets to evaluate them on, and they're just an important like machine learning model that's widely used. So that's why we started there. But for instance, it would be really interesting to evaluate these data sets also from the perspective of generative modeling.
Absolutely. Well, thank you so much for your time and for this presentation today.
Thank you.